Hi, this is Ms. Fitzmaurice. This video is an introduction to angular kinematics. So angular kinematics are really similar to the kinematics that you used at the beginning of the year. All the equations are almost exactly the same, but I need to spend a little bit of time defining some angular quantities, and then I'm going to compare the angular quantities and angular equations to the ones you're used to seeing in translational kinematics. And translation just means that it's motion in the x and y direction that doesn't involve rotation. And then I'm going to talk about the basics of rolling. So rolling, as you can imagine, if I have a ball and it's rolling, it will both rotate and its center of mass will move at the same time. So it's kind of a combination of rotational and translational, the old kind of movement we are used to seeing. So angular motion is actually pretty much the only time in physics where instead of using degrees, we're going to use radians. And so these are the symbols we're going to be using. Of course, the theta is our angle. It's how many radians your object has rotated through. Okay. Omega is called your angular frequency or your angular velocity. And it's basically the analogy of speed. It's how many radians this is not how you spell through, rotated through per second and then alpha, as you saw in the last video, is your angular acceleration and the main idea is it's radians, or let's say that it's the change in angular velocity per second. Okay, so the units, theta is just going to be in radians, omega, okay, your angular velocity will be in radians per second, and of course your angular acceleration will be in radians per second squared. Sort of as an analogy to kinematics, I'm going to put this over in the side. You can think of theta as like your position. Okay, angular velocity is like your velocity, and angular acceleration, of course, is like acceleration. And so you might feel like, oh my god, I have to learn a whole new set of kinematics equations. This is awful. But actually, if we go to the kinematics equations that we have known forever, and everywhere we had an x, we put in a theta, and everywhere we had a v, we put in omega, and everywhere we had an a, we put in alpha. We actually get the right equations. So I'm going to go ahead and I'm just going to write our normal translational equations that we're used to. So we're used to x equals x naught plus v naught t plus 1/2 a t squared. The rotational version of that is going to just be almost the same, except for x I'm going to put theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And for my second equation, v squared equals v naught squared plus 2a x minus x naught, I'm going to go ahead and I'm going to put in omega squared equals omega naught squared plus 2 times alpha theta minus theta naught. Okay, so hopefully you can see these are pretty much exactly the same equations. And then lastly, for v equals v naught plus a t, I also have omega equals omega naught plus alpha t. Okay, and then a quick note about positives and negatives. Okay, just like torque, if you have an angle and you are rotating counterclockwise, then theta is positive. Okay, if you're rotating this way, then theta will be negative. So it's the same rule as torque. Okay, and the same thing is going to go for omega and alpha. Those will follow the same rules. Okay, so it's just the same as your torque. Okay, so let's say that we have something and it is rolling. Okay, so maybe I have a bicycle wheel, and my bicycle wheel is going to be rolling along. You know, it's rolling in this direction, and we'll say that it's rolling with a constant alpha, a constant angular acceleration. How can I relate the angular velocity, omega, to v, my actual velocity? And to think about that, I need to think about a dot on the edge of my wheel. Okay, so as this thing rolls in this direction, eventually, sometime later, the dot, okay, that part of the wheel will now be on the ground. And if my wheel is rolling without slipping, and I'm not a very good artist, you have to forgive me for that, okay, but if this thing rolls without slipping, then the distance that this thing has rolled in between the time when the dot was up here and the dot gets the ground is going to be the same as, so I mean this distance right here, that should be the same as the blue distance that I'm drawing along the wheel. Okay, so I'm going to name this along the wheel D1, I'm going to name this D2, and we expect those should be the same distances. Okay, so we'll set D1 equal to D2, and let's say we know that in that time we've gone through an angle theta. Okay, so if we wanted to calculate D1, the area around the circle that we have traveled, we have to think about the circumference of the circle. Okay, so actually we know that for a whole circle, we will have traveled 2 pi r around the circle, And for theta, the distance we've traveled, so that's for d1, it should be 2 pi r times the fraction of the circle we've gone around, so that's theta divided by the radians around a circle, which we all know is 2 pi. Okay, so actually the distance we've traveled is r times theta. Okay, so I know that r times theta is the distance that I've gone. And if I want to divide by time, I can divide both sides by time, and that's totally legal algebraically. And what I get is r theta divided by t equals d2. But theta divided by t kind of reminds us of omega, so I have r omega is equal to dt. d2 divided by t kind of reminds me of v. Okay, so if I have rolling motion, then these things are true. Okay, the distance times my angle is equal to d2. Okay, and r omega is my velocity, kind of extending that out one more. If I have some kind of acceleration, and I'm going to say this is the tangential, not the centripetal acceleration, okay, because it's going to be like the acceleration in this direction is going to be r times alpha. So if you want to convert, if you're rolling and you want to convert between distance and angle, or velocity and angular velocity, or angular acceleration and regular acceleration, you basically just multiply by r. Alright, so I know, again, this is a lot to take in one sitting. I want you to write down a couple of questions that you have for tomorrow, and I want to talk about those questions tomorrow. Tomorrow in class, we're going to be trying some problems relating to these. So come with questions, and hopefully at the end of tomorrow, you will get a better sense of both this angular kinematics and also the relationship between torque, moment of inertia, and angular acceleration.